Welcome back to an introduction to Earth Science. I'm your professor, Dave Cocchiarella. This is the textbook, Foundations of Earth Science, the 8th edition. And this is Chapter 8, Geologic Time. We've talked about plate tectonics, earthquakes, and mountain building, volcanoes, and other igneous activity. Now we're going to begin to define those great spans of time that we have to understand when we start talking about plate tectonics. This chapter starts with a very brief history of the science of geology, and we'll start in the mid-1600s when geologists were trying to determine the age of the Earth. And they had a number of different ideas, and then came along Archbishop James Ussher, who was a biblical scholar, but a learned man and a scientist of his own right. And he looked at Scripture, and he decided, based on Scripture, the Earth was formed about 4004 BCE. Now, that's before current era. In those days, they referred to it as BC, before Christ. And his date came from Scripture. It's actually a day in October of 4004 BCE. Using that 6,000-year time frame, that is where we developed this idea of catastrophism. And this is the idea that Earth's landscapes were formed by great catastrophes. And there could have been a series of them, but our current Earth that we are dealing with, the oceans and the lakes and the valleys and the mountains, and even the glaciers, were all what was left over after Noah's great flood. And catastrophism was used to fit the rate of Earth's processes, what we actually saw happening on Earth in terms of erosion and deposition and movement of sand by the oceans, to fit that rate of Earth's processes into the prevailing ideas as to the Earth's age. Then in the late 1700s, a gentleman farmer in England named James Hutton looked around his landscape, the land that he owned, and he wrote the theory of Earth based on his concept of uniformitarianism, which basically says that everything that's happening now happened in the past. So all processes, whether physical, chemical, or biological, not only operating today, but operated in the past. He essentially came up with the idea that geologic processes have been occurring over an extremely long period, because he saw sedimentation, he saw erosion happening on the hills on his farm, he saw it moving through the stream on his farm, he saw the sediment moving in and then downstream to the oceans. He saw it happening, and he knew that it must be changing the landscape, but he also realized that it must take an extremely long time for that to happen. And he wrote that the present is a key to the past, and when looking at the age of the Earth, he felt like there was no vestige of a beginning and also no prospect of an end. Well, today we have developed a keen sense of geologic time, and we've really narrowed it down to a 4.6 billion year time frame. And we've done so using two systems, relative dating and numerical dating. Now, today, radiometric dating, that numerical ages of rocks, allows scientists to very accurately determine the age of rocks, representing very important events in Earth's past. Prior to that radiometric dating, there really wasn't a reliable way to determine the age of the rocks. What scientists did, though, is they created a relative time frame. What happened first, what happened next, what happened after that. Numerical dating doesn't replace relative dating. It actually just works to supplement it. The two work together. So using the two together, we've come up with a very specific geologic time scale. Now, the principles that allowed relative dating to work and to develop a time scale of the Earth, there's a number of them, as you can see. And these are all principles of how rocks form and how they act. The principle of superposition, which says in a layer of flat rocks, the oldest rock is on top and the youngest rock is in the bottom. The principle of original horizontality, no matter how rocks may look today, bent or folded, that all sedimentary rocks were deposited flat. Principle of lateral continuity, that sedimentary beds are continuous. The principle of cross-cutting relationships, that cross-cutting features will be the youngest features in strata. And then the principle of inclusion, saying small inclusions in rocks are older than the rocks themselves. And the principle of unconformities, which talks about the breaks in the fossil record. And then the last, the principle of fossil succession, which essentially tells us that time and specific time frames can be recognized by looking at fossils in rock. So let's go through all of those. The principle of superposition, developed by Nicola Steno in the mid-1600s, studying sedimentary rocks in Italy. He basically said in an undeformed sequence, meaning these rocks are still flat, of sedimentary rocks, each bed is older than the one above it and younger than the one below. So the oldest bed is on top, the oldest bed's on the bottom, and the youngest bed is on top. Now this also, he determined, applies to lava flows and ash beds. Here you can see the top of the Grand Canyon, and we see all these flat beds of strata, all different types of sedimentary rock, and what we know is the oldest beds are at the bottom and the youngest beds are at the top. The next principle was the principle of original horizontality, which said that no matter how rocks may look folded and bent or doubled over, that layers of sediment are generally deposited on a horizontal plane, in a horizontal position. And rock layers that are flat have not been disturbed, and folded or inclined rocks must have been disrupted after deposition. Some type of deformation occurred to get those flat beds, which is how they started, to look like that. The principle of original horizontality. This principle of lateral continuity said that within a basin, sedimentary strata is going to continue in all directions until it either comes to something else that limits it, or it thins out and ends at the margin of a basin. And what that tells us is that the Grand Canyon, even though we have this gigantic canyon that may be cut into the sedimentary beds, we know that at one time, because of the principle of lateral continuity, that those beds stretched across its entire region. Sedimentary beds originate as continuous layers that extend in all directions. Identical strata of two sides of the canyon were continuous before the canyon was carved. So layers either end by thinning out on the margins of a sedimentary basin, or they end by gradually grading into a different kind of sediment. And this can happen when the same location maybe is at a different level of sea level, where maybe it's much shallower here and then much deeper here because of sea level change. What are cross-cutting relationships? What are cross-cutting features? Well, you get sedimentary rock that's laid down flat, and then some type of faulting occurs, and that fault, that line of the fault, is the cross-cutting item. And then we know that this rock was laid down flat, and then the fault happened after it. Just like with this strata, we've got sedimentary rock, and then two igneous dikes. And what we know about the sedimentary rock is it was here before those igneous dikes were forced into it, before they were intruded into that rock. And so the youngest feature here is this igneous dike. So geologic features that cut across rocks must form after the rocks they cut through, such as faults and igneous intrusions. The principle of inclusions tells us that fragments of one rock unit enclose with another, which is what an inclusion is, that the rocks that contain inclusions is younger than the rocks that provided the inclusion. So in this situation, this is an igneous intrusion, all right? This is light brown. This green it's probably metamorphic the way it's all squiggly. So the metamorphic rock was there, and the igneous magma chamber that cooled into an igneous batholith or just a pluton, it incorporated chunks of that metamorphic rock. And so what we know is this igneous intrusion is younger than the actual metamorphic rock that it included. Then both this metamorphic rock and this igneous rock had to have been eroded away, and then sedimentary layers were laid down on top of it. So this is a sedimentary layer that has pieces of the metamorphic rock and the igneous rock again. And what we know again is that the sedimentary rock is younger than the actual inclusions that are inside of it. And so that's the principle of inclusions, which again helps with relative dating principles. Unconformities also help. Layers of rock that have been deposited without interruption, so no interruption, they've not been deformed, are called conformable. They conform, right? A complete set of conformable strata for all of Earth's history does not exist. There's nowhere on Earth where there's rocks that lie flat from top to bottom, showing the complete history of the Earth, all right? All strata are interrupted in some way. So interrupting the deposition of sediment creates a break in the rock record called an unconformity. And it represents a period where deposition stopped and erosion occurred and then deposition resumed. Generally, uplift is what causes deposition to stop. So generally, rocks in a marine environment are seeing deposition. If those rocks are uplifted, and they are uplifted above sea level, then deposition will stop and erosion will start. And then that same layer of rock would have to subside back underneath the level of the ocean or the sea for deposition to resume. So that type of activity has to happen for unconformities to exist. Three types of unconformities: an angular unconformity, a disconformity, and a nonconformity. An angular unconformity consists of tilted or folded sedimentary rocks that are overlain by younger and more flat-lying strata. So what we've had here is some sedimentary rocks. We've got some sandstone and some shale down here, and it was laid down flat, and then the deposition stopped, and some deformation occurred, lifted it up almost vertical, and some erosion occurred, and then new sedimentary rock was laying down on top of it. And so this is an angular unconformity. Here's another example of an angular unconformity here. We had deposition of this, essentially flat-lying rock, and then it was uplifted up out of the ocean and bent upward, and then there was a whole erosional period that eroded it down to here, and then it came underwater again, and there was new deposition. And so this is the angular unconformity here. The disconformity is simply a break in sedimentary rock strata representing a time when erosion occurred. So sedimentary rocks were laid down, and then there was an end to the deposition of sedimentary rocks, some type of erosion going on, which represents a gap in the geologic rock record during a period of no deposition and erosion. And sometimes they're difficult to find because the layers remain parallel, but they can provide evidence of erosion of some type, and they represent, again, a span in time in which there is no rock record, so a break in the geologic time. And then last we have the nonconformity, which is younger sedimentary rock on top of older metamorphic or intrusive igneous, not extrusive, but intrusive igneous rocks, a rock that formed underground. So both the metamorphic and the intrusive igneous here both formed underground. It implies a period of uplift of deeply buried rock. So the igneous and the metamorphic formed well beneath the surface. For this formation to have occurred, there had to have been a period of uplift when this was all lifted up and then erosion back down, followed by a period of additional sedimentation in which younger sedimentary layers are deposited on top of that erosion surface. The book actually has a couple of really nice examples where it will go through some of these relatively dating processes with sedimentary rocks. Of course, the Grand Canyon is one of the world's greatest history books of sedimentary rock, where each layer is a different page in history. A lot of different things have gone on. And in the Grand Canyon, you have all three types. You have a nonconformity, well, you have several nonconformities. You have a disconformity where there's just a break in sedimentation. There was sedimentation, and then some erosion, and then it restarted up again. You have an angular nonconformity, or I should say an angular unconformity here, where this rock was tilted and then eroded down, and then sedimentation started on top of it again. And then you have the nonconformity as well, where you have your metamorphic and igneous rock overlain by younger sedimentary rock. So the Grand Canyon is an excellent example of unconformities. And then lastly in the book, there is this detailed discussion of this hypothetical region and how the relative dating principles can be applied to the rock strata in this region to determine what has happened. Now, what it tells us is what happened first and then what happened last. It doesn't actually tell us the dates that any of this happened, but when we look at this, geologists will look at this, and what they would determine is, in a marine environment, sedimentary rock A, B, C were laying down, and then E on top of that. So beneath the ocean, A, B, C, and E deposited in that order. That would be the law of superposition. Then there have been some uplift and intrusion of a sill. So what that means is that some uplift has occurred, which has lifted this up out of the ocean. Now it's above the ocean, and an intrusion of an igneous sill was in place. So that is intrusive igneous rock. And we know that the sill D is younger than the beds C and E because the inclusions of the sill fragments from beds C and E. So we're going to have inclusions of these fragments, all right? The next thing that happens is this dike forms, this dike F. And again, this is a cross-cutting feature. And because the dike cuts through A through E, including the igneous, it must be younger. Again, the principles of cross-cutting features. And then layers A through F, including the dike and the sill, are all lifted. They're exposed and lifted, tilted, and some erosion occurs. And then next, all of these beds, G, H, I, J, K, are laid down on top of that, producing an angular unconformity. And again, the book goes through this in detail for you, but it's an excellent example about how relative dating principles can help decipher an area of geologic formation. Next, we move on to fossils, evidence of past life. Fossils are the remains or traces, oftentimes just traces, of prehistoric life. And they are very important time indicators. They can tell us when that rock formed based on the fossil. Once we know when that fossil, that creature that created that fossil lived, we know when those rocks formed. They play a key role in helping to correlate rocks of similar ages that are in far distant locations on Earth. If you find a certain type of rock with a certain type of fossil, and that fossil only lived in a short period of time, you know that rock was formed during that short period of time. So paleontology is the scientific study of fossils. It attempts to understand the succession of life over vast spans of time. Archaeology, on the other hand, studies the material remains of past human life. Now, fossils can be preserved in many ways. There's pure mineralization, there are molds and casts, there's carbonization and impressions. Fossils can be preserved in amber, and there are trace fossils. And some remains of an animal may be altered, and some may not be altered at all. All right? Teeth, bones, and shells may not be altered at all. In some very rare occasions, the entire animal, including the flesh, can be fossilized, like mammoths that are found frozen in Arctic tundra. There's also these mummified slots in dry caves in Nevada where they have found creatures as well. So sometimes the remains of the animal are not altered, but most often in your fossilization they are. So permineralization is when mineral-rich groundwater permeates the porous tissues of some creature that has been buried in sediment, turning into sedimentary rock. Petrified wood is a great example of this. And petrified wood, the mineral that gets into the porous tissue is silica. Petrified literally means turned to stone. Other types of fossils includes molds. Molds where a structure is buried in sediment, was dissolved by the groundwater, and it just literally leaves a mold behind. Only the outside shape and surface markings are preserved. There's no internal structure. Sometimes those hollow spaces of molds are filled with mineral matter, and then you have a cast that is formed. Carbonization, the remains are encased in sediment, and then pressure squeezes out all the liquid and gas until only a thin residue of carbon remains, and that's effectively like an image. It just preserves the image, and it also preserves more delicate creatures and also leaves, and the impressions actually show a pretty considerable detail. You may remember amber from Jurassic Park. They found little bits of dinosaur encased in amber, and that's where they got the DMA from. Amber is a hardened resin of ancient trees. It seals organisms from the atmosphere and the water, and it's also fairly pressure resistant, so it can preserve entire organisms, and more specifically, it can preserve delicate organisms like insects. And then there are trace fossils, traces left behind of animals, indirect evidence like their tracks or their burrows. Coprolites are stuff from their stomach and intestines. Dung can actually be petrified and be a result in a fossil. And then you have gastroliths, which are these polished stones. You may not realize this, but some ancient creatures actually swallowed stones, and that's how they ground up the food that they ingested. We have teeth, they had stones. There are specific conditions that favor preservation of fossils. Only a very small fraction of organisms are actually preserved as fossils, but it requires the rapid burial, and it requires hard parts, meaning bones or teeth or shells, for fossil preservation to occur. Soft parts of animals oftentimes decompose or are eaten, and of course rapid burial from sediment is going to protect organisms from that destruction. So rapid burial is important, hard parts are important, shells, bones, and teeth are much more common in the fossil record than soft parts of animals, which means the fossil record is kind of biased, because if a creature doesn't live somewhere where rapid sedimentation could occur, or that creature has hard parts, the creature might not be saved in the fossil record at all. So what types of organisms are most likely to be missing from, or are very rare in the fossil record? You know, things that are soft, like insects, or things that maybe lived where no sedimentation was occurring at all. They died and nothing buried them, then they very likely were not preserved in the fossil picture at all. So this can create a very biased picture of what life on Earth was like because of the bias of fossilization. So fossils are excellent at helping in correlation. Correlation is the matching up of rocks of similar age but in different regions. So we can use correlation to realize that these rocks were formed in a similar age, but they were formed in different regions of the world, sometimes on different continents. Correlation reveals a more comprehensive picture of the sedimentary rock record. You can do correlating by sort of walking along the outcropping edges within a limited area, and you can see the same type of sedimentary rock, maybe in different places, in different spots in that area, and you can correlate those sedimentary rocks and know that they're both formed in the same area. Rock layers made of distinctive materials can be identified easily through correlation, and then when you add in fossils, you can then correlate rock layered from widely separated areas. And here's an example of some correlation. So you're looking at the northern parts of Arizona and then southern Utah, pretty widely, space in between these areas, several hundred miles. And what we realize is this one continuous layer of sedimentary rock is in all of these different locations. So here's Bryce Canyon, here's Zion National Park, and here's the Grand Canyon. Not every layer exists, but there's correlation, and you have correlation between the very top of the Grand Canyon and the very bottom of Zion National Park. And then again, the top of Zion National Park correlates with the very bottom of Bryce Canyon. And we can determine, or have determined, that the schist at the very bottom of the Grand Canyon is actually Precambrian and Cambrian origin. And we go up in time and we see that the very top of the Grand Canyon is from a Triassic region. And that tells us that these rocks over here in Bryce Canyon, at the bottom of Bryce Canyon, are also from the Triassic region, and so on and so on. So that's the correlation of rock layers using fossils and fossilization. When did we first begin to realize that fossils could be so useful? Well, this guy named William Smith, he was an engineer, and he was actually building canals all over England. And as he dug these canals, he noticed that rock formations in canals, when he dug out the canals, contained fossils, unlike the fossils above or below, meaning he'd find a layer of rock and it'd have a certain type of fossil, and then a layer of rock above that would have a different type of fossil, and the layer of rock below that would have a completely different type of fossil as well. He realized that distinctive fossils can be used to identify and correlate widely separated sedimentary strata. If he found one type of fossil and a type of rock in this canal, a different canal a long way away that might have that same type of sedimentary rock, he knew that they were formed at about the same time. And thus led to the last principle in relative dating, which is the principle of fossil succession. Fossil organisms succeed one another in a definite and determinable order. Therefore, any time period can be recognized by its fossil content. That means that trilobites didn't live in one era in one part of the world, in a different era in another part of the world. And dinosaurs lived in the very deep ancient past in one part of the world, and just in the last century in a different part of the world. We know that fossils come from a very specific time period, and that time period can be recognized by fossil content. Fossils document the evolution of life over time. They are in a very specific succession. And we have some organisms that are dominant organisms on Earth. If we look at fossilization, we can come up with these vast spans of time that we can call ages. There's the age of trilobites, and there's the age of fishes. And after the age of fishes came the age of coal swamps. And then after the age of coal swamps came the age of reptiles, including the dinosaurs. And then the dinosaurs went away, and it was the age of mammals. And we can see that same succession of dominant organisms on every continent. And so you have to ask yourself, what caused these transitions? And we know that these transitions can be seen very specifically in the rock record. And as a matter of fact, when we look at the geologic timescale, what we'll recognize is those divisions of record are based on these transitions. And sometimes it was mass extinctions, and sometimes it was other transitions that occurred. But you can see those transitions in the rock record. So we have a special kind of fossil known as an index fossil, which is really excellent at helping with correlation. But it has to be very special. It has to be a type of creature that existed in a wide geographical space, meaning it would be found in lots and lots of different places, perhaps all over the world, but also found in a very limited short time span, meaning you might be able to find it anywhere and then know that that fossil existed only in a very short time span. So if you find that fossil in a rock in North America or South America or in Asia or in Australia, that no matter what, because it only lived in a short time span, you know that rock formed in that time span. So it's very important for correlation. And where index fossils don't exist, you can have fossil assemblages, which is groups of fossils that occurred in the same time frame that you can also use to correlate different rock strata in different parts of the world. So fossils are great for establishing time. They also are great for establishing environmental indicators. Was the rock laying down in an oceanic environment? Most sedimentary rock is, of course, but there could be some type of continental, if you're talking about ash or even lava flows. Deep versus shallow water. Fossils can also tell you the temperature of the water. They can tell you what type of an environment the fossil lived in. So fossils not only can tell time, but they're very useful in indicating the type of environment. So here's a fossil assemblage. And what essentially we know that if we have trilobites with these other fossils, then it's going to be coming from this older time period. But if we have a dinosaur head with the same type of fossils, then it's going to be coming from a much younger time period. So we can determine the age of the rock using those fossil assemblages. All right, so that was a conversation about relative dating, using all those principles, and then using fossils for correlating. We have the ability since the 1900s to assign specific dates to most rock strata, most types of rock, using the power of the atom. And just a quick review of the basic atom. Every atom is made up of protons, neutrons, and electrons. The protons and neutrons make up the nucleus, and they represent virtually all of the mass of the atom. And then the electrons, which have a negative charge, zip around in shells around the nucleus. Neutrons have no charge, and protons have that positive charge. So almost all of the atom's mass is in the nucleus, so electrons virtually have no mass whatsoever. And I pulled out just a chunk of the periodic table so we can refresh ourselves and know that the atomic number is this top number, the atomic symbol is the letter, and the atomic mass, which is the protons and the neutrons added up, is below the symbol, and then the name of the element, in this case, is boron. So the number of protons in the nucleus identifies the atomic number. So this nucleus has 5 protons, which means it should have 5 neutrons as well, and 5 plus 5 is going to equal 10, which is where you get your atomic mass, is somewhere around 10.81. So go back to hydrogen. Hydrogen just has a 1 proton in the nucleus and 1 electron. So a proton weighs 1.008 atomic mass units. So it's not an exact number, doubling the number of protons to get what your actual atomic mass is going to be. And then some elements have different numbers of neutrons in the nucleus. So there are some complications to that. But the number of protons plus the number of neutrons in an atom equals that mass number. And again, typically you're going to have an equal number of protons and neutrons. And the reason why, as you may recall, you're going to have an equal number of protons and neutrons is because protons being positively charged would not stick together in this this nucleus, because remember, like charges are going to repel each other, so the neutrons act as a buffer. So typically you have an equal number of the two. But again, as in all chemistry, there are always exceptions to that rule. And as I said, those exceptions become isotopes. So some isotopes have an unstable nuclei with bonds that are not strong enough to hold the protons and the neutrons together. There's not an equal number of the two. These nuclei will break apart and decay in a process that we refer to as radioactivity. So radioactivity is where you have one of these unstable nucleuses that wants to become stable, and the breaking apart of that nucleus, the decay of that nucleus to try and achieve a stable state, is radioactivity. And there's three common types of radioactivity, and this is getting sort of deep into this, but let's just try and follow the explanations. There's an alpha particle radioactive decay, a beta particle radioactive decay, and there's electron capture radioactive decay. An alpha particle is literally two protons and two neutrons from the nucleus that leave the nucleus. And that means the mass number is reduced by 4, and the atomic number, remember the atomic number is the number of protons, is reduced by 2, right? Beta particle radioactivity is when an electron from the neutron is ejected. The neutron is actually a proton and an electron combined, the two combined. So if you get rid of an electron from the neutron, that neutron becomes a proton, and the mass number remains the same, but the atomic number is increased by 1 because now there's an additional proton. Electron capture, you capture by the nucleus and combine with a proton now to form a neutron. The mass number remains the same, but the atomic number decreases by 1. So let's look at that specifically. So in your alpha emission, you've got your unstable parent nucleus with your protons and your neutrons, and it gets rid of an alpha particle, which changes the atomic number, the number of protons, by 2, and changes the mass number by 4. And that is radioactive decay and part of a unstable isotope's attempt to become stable. In beta emission, the nucleus gets rid of an electron, a beta particle. The loss of the electron from the neutron causes that neutron to become a proton. So now you've got a proton where you've had a neutron, and so that's an increase in the atomic number, but no change in mass. And the other way is a nucleus capture of an electron, which converts a proton into a neutron. The electron combines with that proton to form a neutron, and that reduces the atomic number because you lose a neutron, so that reduces the atomic number. And those are the different types of radioactive decay. And what this looks like with uranium-238 is you get an alpha emission, and you take your atomic number from 92 down to 90, all right? It's your alpha emission. You're going to take your atomic number down by 2. You lose 2 protons and 2 neutrons, all right? But that doesn't quite make this stable. Now you've got 234, and it uses beta emission to get to uranium-234. And then once again, you're getting a number of alpha emissions to get to lead-214. But the process continues until you ultimately get to lead-206. Lead-206 with your 82 atomic number, or your 82 protons and 82 neutrons in the actual nucleus. But it took all these steps, and that's all radioactive decay. And of course, radioactive decay gives off energy in the form of heat. It gives off radiation, other types of radiation. Heat is radiation. But almost as importantly is this radioactive decay takes a very specific amount of time. And it's that very specific amount of time that we can use to radiometrically date rocks. So when we look at radioactive decay, you start with a parent isotope and you result in a daughter product. There is uranium-238 as a parent isotope. It's an unstable radioactive isotope, and the daughter product is with the stable isotope resulting from radioactive decay. So uranium-238, the radioactive parent isotope that decays in several steps to become the stable daughter product, lead-206. And when we talk about the time it takes that decay to occur, we talk about it in terms of half-life. So Radiometric dating is the reliable method of calculating the ages of rocks using the rate of decay of isotopes, because those rates of decay for many isotopes do not vary at all. They're exactly the same at the Earth's surface. The rate of decay for those isotopes has actually been precisely measured. We know those rates of decay, and we can measure the amount of daughter product as compared to the parent isotope in a given rock. When the daughter product has been accumulating at a known rate since rocks were formed, once we measure the amount of daughter product that's there, then we know how much radioactive decay has occurred. And of course, knowing how long it takes for the radioactive decay to occur, we can tell how long that rock has been in existence. A half-life is the time required for 1/2 of the nuclei in a sample to decay. It's a half-life. One half-life has transpired when the quantities of parent and daughter material are equal. There's a 1-to-1 ratio. And a half-life of an isotope is known, and parent-daughter ratio can be measured, then the age can be calculated. If you know the half-life, which we've said we do know the half-life, and we can measure how much of the daughter and parent ratio there are, and we said if we can do that, then we can know the age of that rock. So let me talk a little bit more about that half-life. So what we're starting out with here is the percent of parent material and the percent of daughter material. So a rock is formed, let me go back here. A rock is formed in the instantaneous moment of crystallization of uranium-238. There's nothing but uranium-238. It's all uranium-238 and no lead-206. It's all uranium-238. So at the moment the rock is formed, crystallization occurs, you have 100% of the parent and 0% of the daughter. One half-life occurs when this process has occurred so that there is 1/2 of the parent left and an equal amount of the daughter has been formed. So 1/2 the parent has formed into 50 atoms of the parent. It's formed into 50 atoms of the daughter. And then the same thing happens in the next half-life. 1/2 goes away, 25 atoms of the parent becomes 25 atoms of the daughter, and now you have 75 of the daughter. And then after this, you get 12, 12.5 go away, and you add that, you get 87, 87.5. The bottom line is the daughter atoms are accumulating while the parent atoms are declining. And so if you were to go in and measure a rock, take a rock, and you found exactly 50 atoms of the lead and 50 atoms of the uranium, you would know that one half-life had occurred. And if you know that half-life, then you can tell how old that rock is. The change is exponential. Half of the parent remains after one half-life, 1/4 remains after 2 half-lives, and so on and so on and so on. So the 5 radioactive isotopes that are very important to geology are uranium-238, 235, thorium-232, rubidium-87, and potassium-40. They go from the radioactive parent to this stable daughter product. And look at these time frames. They are truly massive. 4.5 billion years. The uranium-235, quite a bit shorter, 704 million years. The thorium takes 14.1 billion years for a half-life to occur. So any thorium that may have existed at the beginning of Earth still hasn't had a half-life occur. And look at this one. It goes to 47 billion years. Potassium is about 1.3 billion years, and potassium is actually a great one to use because there's tons of potassium in rocks in the crust, so we can use that one well. So one of the really key components of this is only useful if the mineral has remained in that closed system. No addition or loss of parent or daughter isotopes has occurred. So what that means is when this 100 atoms of uranium form, crystallize at the very beginning moment of the rock, through this whole half-life, which is a pretty darn long time, that means you've not taken away artificially any of those atoms, nor have you added artificially any of the daughter atoms. It has to have occurred in a closed system. So radiometric dating methods have been used to determine the age of some of the oldest rocks on Earth. 3.5 billion year old rocks have been found on all continents, all right? The oldest rocks, 4.28 billion years, have been found up near Hudson's Bay in Quebec, Canada. So on North America, we own the oldest rocks on Earth. We found 3.7 to 3.8 billion year old rocks in Western Greenland, 3.5 to 3.7 billion year old rocks in the Minnesota River Valley and in northern Michigan. Africa has these 3.5 billion year old rocks, and Western Australia has 3.5 billion year old rocks as well. So this radiometric dating has been very effective at helping us date the oldest rocks on the planet. Now, carbon also exists as an isotope, and it has a very short half-life. Well, the good news about carbon is since carbon dioxide is taken in by plants and animals take in plants, then all animals have carbon dioxide in them, and all animals have carbon-14 in them. And the carbon-14 in your body is constantly being replenished. And so when you die, or I should say any animal dies, as the carbon-14 begins to break down, we can use this very short half-life of carbon-14 to age remains, sometimes biological matter, and even some in plant life as well, for many tens of thousands of years. So it's useful for dating events from historic past and very recent geologic history. So not prehistoric, but recent past. Carbon-14 is present in small amounts in all organisms. Again, in the upper atmosphere, carbon-12 is broken down, carbon-14 is created, it binds with carbon dioxide is taken in by plants, and then in some form or the other, all animals take in plants. And so pretty much all organisms on Earth have carbon-14 in them. All right, lastly, in this chapter, we're talking about the actual geologic time scale, that multicolored chart that you may have seen before. And it's a pretty complicated chart. It has a lot of information on it and a lot of numbers on it. But really, as you get to know it and you learn how to read it, it really is pretty fascinating when you consider the spans of time we're talking about. So geologic history is divided into units of variable magnitude. The longest of those units are eons, and they represent the greatest span of time. We are currently living in the Phanerozoic eon, which began about 541 to 542 million years ago. And the Phanerozoic is a word that means visible life, because the point at which we move from the eon prior to the Phanerozoic, the eon prior was the Proterozoic, to the Phanerozoic, was a point at which in the rock record we began to see a lot of fossils. Prior to that point, prior to 542 million years ago, there were very few fossils, and the fossils were single and multi-cell organisms. And suddenly, about 542 million years ago, there was an explosion of what we refer to as shelly fauna. And shelly fauna are just fossils of animals that had hard parts. And the Phanerozoic eon began with that Cambrian explosion about 542 million years ago. And since that time, we have much more detailed information. Now, our eons, our Phanerozoic, our Proterozoic prior, our eons are divided into eras. Now, the Phanerozoic eon is divided into the Paleozoic, the Mesozoic, and the Cenozoic. And Paleozoic means ancient life. Mesozoic, which is the time that ended with the dinosaurs, means middle life. And Cenozoic means early life. And Cenozoic essentially is the age of mammals. And all of these divisions are bounded by profound worldwide changes in life form. All these divisions within the eras. And again, old life, middle life, and young life. Each era is also divided into periods, and periods are divided into epochs. And so when you read the geologic timescale, you're literally reading the history of Earth, not just back the 542 million years that makes up the Phanerozoic, but the entire 4.6 billion years of the Earth's history. So the eon is the largest span of time. You have the Archean, the Proterozoic eon. Both of those eons together are casually known as Precambrian. Then the Phanerozoic eon, where we are now, again, that dividing point somewhere around 541 to 542 million years ago. So this is all of geologic time from the beginning of Earth to right now. And if I take just the Phanerozoic eon, that Phanerozoic that means visible life, and I break it into this largest section over here, the Phanerozoic eon is, of course, predated by Precambrian times. The Phanerozoic is known by eras of Paleozoic, Mesozoic, and Cenozoic, ancient life for the Paleozoic, middle life for the Mesozoic, and recent life for the Cenozoic. Now, each of these eras, Cenozoic, Mesozoic, and Paleozoic, are also further broken down into periods, and then each of the periods are further broken down into epochs. And you see that prior to the Cenozoic, the Mesozoic, and the Paleozoic, they do not have named epochs. These different periods are just early, middle, and late, because again, the further back you go in time, the less detail you have, the earlier you are, the more detail you have. So we have the most detail from about 66 million years ago. Now, 66 million years, 65 to 66 million years should be a number that will be familiar to some. This is when, hypothetically, a giant asteroid struck the Earth and killed off the dinosaurs. And we went from our Mesozoic, our middle life, to our current life. And the era of Cenozoic was broken down initially into Tertiary and the Quaternary, but the Tertiary is now gone away, and that's been broken down into the Paleogene and the Neogene. So this is now a casual terminology, just in the same way as the Carboniferous represents what's the Mississippian and the Pennsylvania, and this is when the coal swamps dominated. But you may also recognize these periods, the Triassic, the Jurassic, and the Cretaceous, and of course this is the age of dinosaurs. The Pleistocene is what is known as the Ice Age, up here between 2.5 million years ago to about 15 to 17,000 years ago. That was the Ice Age, when we had that series of glacial periods interspersed with interglacial periods that would be warm. The glacial periods, of course, very cold. And the Holocene is the time of modern man. Now, some geologists believe that we've left the Holocene and we've gone into what's known as the Anthropocene, and that is a period marked in which man has actually had an impact on the environment and therefore an impact on the rock record, but that's still to be decided. So the most detail on the geologic time scale begins at about 541 to 542 million years ago, and prior to that time we have much less detail. There are 4 billion years prior to the Cambrian that are known as the Precambrian, and those are divided into the Archean and the Proterozoic eons, and together they represent about 88% of all geologic time. So really we're only living that 542 million years since we started to see these ancient creatures and fossils. It only represents 12% of the span of time of Earth's history. Now again, some unofficial terms like Precambrian, Haden. Haden is those earliest eons, or the earliest eon of Earth's history before any of the oldest rocks have been measured, and Haden refers to essentially Hades or hell. The geologic time scale has to be updated periodically to include changes in unit names and boundary age estimates. That's as new information and new details come to light, and that is done on a regular basis. Cenozoic was divided into the Tertiary and the Quaternary, and so now the Tertiary is divided into the Paleogene and the Neogene. So there are changes that can be made. Rocks can only be radiometrically dated if all the minerals of that rock formed at the same time. And really, that is only an absolute for igneous rocks. Igneous rocks cool, and when they cool, they crystallize. And when they crystallize, those minerals make up rocks, and that is when the parent material is created. Sedimentary rocks, they're not formed that way at all. Sedimentary rocks are lithified from the fragments of old rocks. And so sedimentary rocks, you can't use radiometric dating, and even metamorphic rocks are difficult. So radiometric dating measures the age of sedimentary rocks incorrectly. It always measures them older than they should be. Sedimentary rocks, of course, contain sediment from previously formed rocks, so they would date older than the age of the actual rock. And so sedimentary rocks, individual sedimentary rocks, can actually contain clasts or sediments from different ages and different periods of time. So radiometric is perfect for igneous, it's pretty good for metamorphic, and it can't be used for sedimentary. So how do you then age sedimentary rocks? Well, you have to sort of bracket sedimentary rocks between igneous rocks. And so in this bed, this is an actual cutaway of an actual bed of rock. You have these formations, Morrison, Somerville, Dakota, the shale, and these other formations. And they are bracketed by this volcanic ash bed that can be dated by 160 million years, and then this igneous dike that can be dated to 66 million years. So we know this Wasatch Formation is younger than 66 million years, and these 1, 2, 3, and 4 formations are going to be older than 66 million, but younger than 160 million, and these formations are going to be older than 160 million. So geologists use datable igneous masses to bracket the age of the sedimentary rocks that form before and after the igneous formations. And so you've got relative dating and then radiometric dating that works together that have allowed geologists to paint this picture, to create this geologic timescale, which again we see here, which is this amazing history of Earth going back 4.6 billion years or 4,600 million years. That was our look at Chapter 8 from Foundations of Earth Science, the 8th edition, written by Lutgens and Tarbuck, brought to you by Pearson Education. And of course, Chapter 8 was Geologic Time. Now we're going to begin to talk about the ocean. And the ocean is so intertwined with the geosphere and the atmosphere and of course the biosphere. It's going to be a fascinating study. So we'll see you for Chapter 9.